Hey guys, today we're going to look at the concept of acceleration and what is acceleration. That's what we have today. All right, so cutting straight to the chase, acceleration is defined as any change in velocity. Okay, so in regular English, we think of acceleration as meaning speeding up, which is true, but there's more to it than that. And again, this more precise definition that we have is in physics, acceleration is any change in velocity, right? Let's see, there's where it is. There it is. Okay. Now, we remember from last week before the snow, that velocity is a vector quantity, which includes speed and direction. Um, so what this means is that in physics, acceleration can be speeding up. That is still acceleration, just like we always consider it. But it can also mean that something is accelerating if it is slowing down, because when something slows down, its velocity changes. So that's an acceleration. Now, we sometimes call that a negative acceleration, slowing down, but it is still an acceleration. Occasionally, we will use the term deceleration for slowing down, but again, it's still an acceleration. And negative acceleration is usually the most common one. But there's one more too, and it's because velocity is speed and direction. Now, for now, you have to take my word for it on this. It will make more sense later when we look more closely at vectors. But acceleration is also a change in direction. So to make this very clear, if you're in a car and you're going around a corner at constant speed, so you're not speeding up, you're not slowing down, you're just going around the corner, that counts as an acceleration because your direction is changing, even if your speed is not. And since velocity is both speed and direction, going around a corner, changing your direction is an acceleration, even if the speed does not change. Okay, now how do we measure this stuff? I wish I had the time here and to write this stuff out. So you're going to have to pause it and see what we got here. Okay, so acceleration is A. It is delta V, which is a change in velocity. Now, this triangle symbol here, that's called a delta. That's the Greek letter delta. And it in physics and in engineering, delta stands for change in. So delta V means change in velocity. And we divide, excuse me, and we divide that by a change in time. Okay, so time is measured in seconds, velocity is in meters per second, and that means that, let's move my picture here a little bit. We have meters per second divided by seconds, which makes a weird unit of meters per second squared. Okay, so acceleration is always in meters per second squared. That's something that I want you to remember, okay, because it will tell you when you see those meters per second squared units to say, hey, that's acceleration. And likewise, when you're thinking of an acceleration, I want you to be able to think in terms of the units of it are meters per second squared. That helps in solving problems and also helps you understand what's going on. So yeah, meters per second squared. That's a strange unit, but there's a way to make a little bit more sense of it here. So here's another terribly neat diagram, but we can use it here. Okay, so what do we mean by this meters per second squared? What is acceleration really? Okay, so I've made a little table here, and we're going to envision a car which is starting from standstill, from rest, as they say. Um, and we step on the gas, and we go faster and faster and faster, and we speed up. That means our velocity is changing, so that means we are accelerating. So if we make a table of this here, at time zero, we're not moving. After 1 second has passed, we're moving 2 meters per second. After 2 seconds, we're moving 4 meters per second. After 3, 6 meters per second, 4 seconds, 8 meters per second, so on. So as each second passes, we're going faster and faster and faster and faster. Now, if we look at the change in speed, delta V, then let's see, let's put this someplace where it's not going to bother us so much. Think that'll work. Okay, so delta V, that's the change in speed. We see that in each time interval, our velocity is changing by 2 meters per second. Okay, so you can see that clearly, but yeah, so each moment the velocity is changing by 2 meters per second. And acceleration is the change in velocity divided by the change in time. So we can look at this and see that 2 meters per second, that's the change in velocity, and that happens in 1 second. So we wind up with 2 meters per second, okay? Our velocity is changing. Our velocity is changing by 2 meters per second each second, or 2 meters per second per second. And for this reason, instead of saying 2 meters per second squared, we will often say 2 meters per second per second. When you look at it this way, 2 meters per second divided by 1 second, this 2 meters per second, it multiplies out to be meters per second squared, and that's where that weird unit comes from, the meters over second squared. But if you think of it in terms of meters per second that the velocity is changing, then that unit may make a little more sense. Now, as we can see here, put this up here, if we take a different time interval, like if we go to 3 seconds, well, now our change in velocity is 6 meters per second, and it happens in 3 seconds. So in this case, it looks like 6 meters per second in 3 seconds, and we wind up with the same value for the acceleration, because in this situation, the acceleration is constant. So it really shouldn't matter what time interval we look at. We should always, the math should drop out to be the same 2 meters per second squared. Okay, so that's how we use that equation and put it into practice. Let's see what else we got. This is an old one. How do we measure acceleration? We just said this one. Okay, let's try this one. How do we measure acceleration? Okay, so imagine a gazelle. It begins from standstill and it's running 28 meters per second after 4 seconds. And what I would like you to do is pause the video here and do the calculation. What is the gazelle's acceleration? I would like you to use the GFEW format for practice. Okay, so pause it here and see if you can figure it out. Okay, we're back. Hopefully you have an answer. So we go from 0 to 28 meters per second in 4 seconds. We're going to find the acceleration in meters per second squared. We start off with our equation, A equals delta V over delta T, and we see that we get 28 meters per second divided by 4 seconds, and it's 7 meters per second squared. Now, what I've done right here, this 28 meters per second minus 0 meters per second, is how we calculate a delta, how we calculate a change. And the way it works, we take the final value and subtract from that the initial value. So this would be V final, the final velocity minus the initial velocity, and that will give us the change in velocity. And likewise, delta T is the change in time. The final value was 4 seconds, the initial value was 0 seconds, because that's when we started the stopwatch, started the clock. So delta V over delta T, 28 divided by 4, 7 meters per second squared. And we do see that we get the unit so we wanted to. So life is good. We got a good answer. All right, I think that's what we've got. Let's see. Right, so let me give you some other characteristics of acceleration here. I'm going to run this down to the bottom. There we are. Okay, so things to remember here. Acceleration is a vector quantity. A is a vector quantity, meaning that it has direction and magnitude. It also, because it's a vector, it can be positive or negative. All right, let's see. And the negative. And let's see. What this means is when acceleration is positive, the thing is going faster. And when acceleration is negative, the thing is slowing down. So that means that you're going to have a velocity in one direction and an acceleration in the opposite direction. An example of this is if I drop this pen, it's going to accelerate toward the ground. We know that happens when things drop. If I throw the pen up in the air, as it's rising, it's slowing down, meaning that its acceleration is negative. Its acceleration is downward, even though its velocity is upward. So that means that when it's going up, its acceleration is downward, and then when it falls downwards, its acceleration is still downward. So acceleration and velocity do not have to be in the same direction. Let's see. And finally, the direction of the acceleration, direction of A is in the direction of the change in velocity. Same direction as change of V, of velocity. All right. So again, when we throw the pen up in the air, the velocity of the pen is slowing, 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 slowing. So the change in velocity is downward. It's not speeding up. It's not going the same direction. It's not going the same velocity. It's slowing down. So the change in velocity is downward, which means the acceleration is down. Okay, that's it. So we've learned some stuff about acceleration, the equation, how we use it, what those weird units, meters per second squared, really means, and some general truths about acceleration. And that should be enough for today. Thanks for your time, and we will see you next time.